1 Introduction to Onto Functions. Hello everyone, let's begin our lesson on onto functions. To start, let's look at the foundation. In our previous studies of relations and functions, we have already established that a function acts as a mapping process, where elements from a starting set, which we call the domain, are paired with elements in a target set, known as the codomain. However, it is important to realize that in a general function, there is no guarantee that every single element in the codomain will be used. In many cases, you may find that some elements in the target set simply do not have a corresponding partner in the domain. This brings us to our main topic. When a function is structured in such a way that it covers the entire codomain, we call it an onto function, which is also known by the mathematical term surjective. To put this in simpler terms, in an onto function, there are no leftover elements in the codomain. Every single element in the target set must be the image of at least one element from the starting set. Now that we have this conceptual overview, we will move forward to the next slide to examine the formal mathematical definition and the critical difference between the codomain and the range. 2. Formal mathematical definition. Now that we have a general idea of what it means for a function to cover its target set, let's move on to the formal mathematical definition. Looking at the first point, we say that a function f from set x to set y is onto, or surjective, if for every single element y in the codomain y, there exists at least one element x in the domain x, such that f of x equals y in plain English. This means that no matter which element you pick from the target set, you can always find a starting value that maps directly to it. To truly grasp this definition, we need to clear up a very important distinction between the codomain and the range, as these two terms are often confused. First, the codomain is simply the set y that is specified as the target of the function. It is the set of all values that could potentially come out of the function. Second, the range is the set of all actual outputs, or images, that the function truly produces when you plug in every possible value from the domain. This leads us to what I call the golden rule for onto functions. A function f from x to y is onto if, and only if, the range of f is exactly equal to the codomain of f. If the range is smaller than the codomain, it means some elements were left out, and the function is not onto. In the next slide, I will use a real-world analogy involving students and chairs to help you visualize this relationship more clearly. 3. Real-world analogy. Now that we have covered the formal definition and the relationship between the range and the codomain, let us use a real-world analogy to make these concepts more intuitive. Imagine a classroom scenario where we have a set of students, which we will treat as our domain x, and a set of chairs, which will represent our codomain y in this case. The function is the process of assigning each student to a chair. Let us examine 3 different scenarios to see how this relates to surjectivity. First, consider scenario A. Suppose there are 30 chairs in the room, but only 25 students. Even if every student takes a seat, at least 5 chairs will remain empty. Because there are elements in the codomain, the chairs, that are not mapped to any element in the domain, the students, this mapping is not onto. Next, let us look at scenario B. In this case, we have exactly 25 chairs and 25 students. If every student sits in a different chair, every single chair is occupied. Since no chair is left empty, the range is equal to the codomain, and therefore, the mapping is onto. Finally, consider scenario C. Imagine there are only 20 chairs but 25 students. If every chair is occupied by at least one student, meaning some chairs might be shared by 2 students, the mapping is still considered onto. This is because the only requirement for a function to be onto is that no element in the target set is left out. As long as every chair is occupied, the condition for surjectivity is met. By understanding these scenarios, you can see that being onto is simply about the completeness of the mapping. Now that we have a conceptual grasp of this, let us move forward to the next slide, where we will learn how to verify this algebraically. 4 step-by-step algebraic verification. Now that we have covered the theoretical definition and the real-world analogy of chairs and students, let us move on to the practical application. To prove whether a function is onto, we follow a systematic algebraic process. Let us walk through an example together. Consider a function f, mapping from the set of real numbers to the set of real numbers, defined by the equation f of x equals 3x plus 5. Our goal is to determine if this is an onto function. Step 1 is to identify the codomain. Looking at the function definition, it is defined from the set of real numbers to the set of real numbers. Therefore, the codomain, our target set, is the set of all real numbers. In step 2, we set the function equal to an arbitrary element, which we will call y by picking any general element y from the codomain of real numbers. We can write the equation y equals 3x plus 5. Step 3 requires us to solve for x in terms of y essentially. We are trying to find if there is an input x that will produce our chosen output y. If we subtract 5 from both sides, we get y minus 5 equals 3x. Then, by dividing both sides by 3, we find that x equals y minus 5, all divided by 3. Now, in step 4, we must verify if this x actually belongs to the domain. Since we defined y as a real number, the result of the expression y minus 5 divided by 3 will also always be a real number. This confirms that for every single y in the codomain, there exists a corresponding x in the domain. Finally, we reach step 5, the conclusion. Since every element y in the codomain has a preimage x in the domain, the range is equal to the codomain. Thus, we can confidently state that the function f of x equals 3x plus 5 is an onto function. Keep this process in mind, as in the next slide, we will discuss some common mistakes students make when performing this verification, particularly regarding the set definitions. 5 common mistakes to avoid. Now that we have walked through the algebraic process of verifying a function, let's discuss some common pitfalls. It is very important to be aware of these mistakes to ensure your proofs are accurate. First, be careful not to confuse the codomain with the range. A frequent error students make is assuming a function is onto simply because it produces a set of outputs. However, you must always check the specific codomain provided in the problem. For example, if the codomain is defined as the set of all real numbers, but the function, such as f of x equals x squared, only produces positive numbers and 0, then it is not onto. This is because the negative numbers in the codomain are left uncovered. Secondly, never ignore the set definitions. You must realize that the same algebraic expression can be onto or not onto depending entirely on the sets involved. Let me give you 2 contrasting examples using the same formula. If we have a function from the set of all real numbers to the set of all real numbers where f of x equals x squared, it is not onto, because negative numbers in the codomain have no preimage. But if we redefine the function to map from the set of all real numbers to the set of non-negative real numbers, meaning 0 and all positive numbers, then f of x equals x squared becomes an onto function, because the codomain has been restricted to only those values the function can actually produce. Finally, do not mix up the concepts of one-to-one and onto functions. While both describe the nature of the mapping, they focus on different properties. Remember that one-to-one, or injectivity, is about the uniqueness of the mapping, ensuring that different inputs always lead to different outputs. On the other hand, onto, or surjectivity, is about the completeness of the mapping, ensuring that every single element in the target set is reached. Keeping these distinctions in mind will help you avoid simple errors. Now, let's move to the final slide to summarize our key takeaways. 6 key takeaways. To wrap up our lesson on surjective functions, let's review the key takeaways to ensure you have a solid grasp of the concept. First, let's revisit the definition. A function is considered onto if every single element in the codomain has at least one preimage in the domain. Essentially, this means that no element in the target set is left out. This brings us to the critical condition we mentioned earlier, often called the golden rule. A function is onto if, and only if the range is equal to the codomain. As we discussed when looking at common mistakes, if the range is only a subset of the codomain, the function cannot be surjective. Regarding the verification method, remember the algebraic process we used in our example. To prove a function is onto, you should express x in terms of y. Once you have isolated x, you must check if that resulting value of x always exists within the specified domain for every possible value of y in the codomain. Finally, for those of you who prefer a visual approach, keep this visual cue in mind. When looking at a mapping diagram, every single element in the second set, which is set y, must have at least one arrow pointing to it. If there is even one element in set y without an incoming arrow, the function is not onto. Review these points carefully, as they will be your roadmap for solving any problem regarding surjective functions.